Sensitivity versus specificity. One of the most annoying conceptual things for many people. The reason I'm going over this, just as a little background, I'm a family physician. I just finished residency about a week ago. So I've finished all my licensing boards and everything, but there's a family medicine board coming up since usually you take that at the end of residency. But because of COVID, it was delayed. So even though I've graduated residency, I still have to take the family medicine board. So I had to go back over sensitivity and specificity last night. As we say in med school, it's good to teach because teaching helps you for the test as well. So that's part of the reason I'm doing it. And if you look at my YouTube channel, I mean, it's a mix of videos, a whole bunch of music. I do a lot of guitar covers, originals, and blues and things like that. I think my most popular video on here was Disorganized Thoughts, which I did for a random kind of psych talk when I was studying for boards in med school. But since that was pretty popular, I guess I can teach medical kind of topics pretty well. So I was going to go over sensitivity and specificity. And the reason I thought it'd be useful is because this is a confusing topic, and a lot of times I think when some people teach it, they just make it even more confusing. And just to kind of warn you guys, you might want to slow this down, watch it multiple times, because you can kind of get yourself in a really confusing mindset if you're not thinking about this in the correct way. So I have horrible handwriting, but I want to show you some things I wrote down since I'm not real tech savvy here. So this is the first thing I wrote down, and this is important to go over before talking about sensitivity and specificity. So in any given test, you can write it out in just a square here, and you put on the x-axis the disease, and on the y-axis you put the test. So for any test, the result can be positive or negative. I guess there can be an indeterminate, but for the sake of any kind of test or anything, this is going to be mostly it. And for a disease, the disease is either going to be truly positive, someone's truly going to have a disease, or they're not going to have a disease. So this gives you 4 possible situations. One situation is a true positive, meaning that the person that actually had the disease actually did test positive for it. You can have a false positive, meaning that the test was positive, but the person actually didn't have the disease. You can have a false negative, meaning that they really did have the disease, but the test was negative. And you can have a true negative, meaning that they didn't have the disease and the test was negative. And anybody going to any medical office for any kind of screening or to see what kind of possible diseases they could have, I mean, these are pretty important. And ideally, you want to have a test that truly shows the positives and truly shows the negatives. And you want to not have false negatives and false positives. So just having that in mind when we talk about this, because when I go through the equations, I'm only going to use these. So think about this for a while. Look at that chart until you really understand it. It's pretty basic, this part. We're not talking about sensitivity and specificity. We're talking about 4 possible situations in any given disease process from a positive or negative test. Let me go back here. So I hope that that's pretty clear. 4 possible situations. I got this new app and just paused the video for a half a second there. So now we're going to get into sensitivity and specificity. So I'm going to flip the screen here again. Now sensitivity equals the percent of people with a disease that is correctly identified. Now that can be pretty confusing, but let's go into what the actual equation looks like. So sensitivity equals the true positives. Sorry for the T and P being kind of separated there. They should just be grouped together like that. True positives divided by true positives plus false negatives. Memorize this. And then I'm going to show you how to conceptualize this. Specificity equals the percent of people without the disease who are correctly identified. Memorize this. True negative divided by the true negatives plus the false positives. Now I'm going to explain what this exactly means. I think, first of all, a good tip to memorize this is when I'm thinking about this, and if you don't want to use any cerebral power at all, you can think about it this way. Everything in this equation is actually a positive. Sensitivity, think positive. I'm going to write that down. All right. Think positive. Okay. Meaning a true positive is really positive, a true positive is really positive, and a false negative means that it's actually positive. Everything here is positive. Now look down at specificity. Everything is truly negative. Meaning a true negative is truly negative, a true negative is really negative, and a false positive is truly negative. So when you're thinking about that, remember that always the numerator has the true negatives for specificity, true negatives for sensitivity, and the denominator will always be that numerator plus the one that will give you a negative for specificity, which is false positive, and a positive, which is a false negative. Now, like I said, again, with what we talked about over here, that there's always 4 possibilities. Now let's see what this is showing us. So what is sensitivity really showing us? I think that this definition up here is really confusing, but I would still know it because you might be tested over that exact thing. The way I think about it is this. A true positive means that the people that had the disease also were truly positive, who tested positive for it. This is what you want. But since this is the denominator, a high sensitivity test would have a low false negative rate. So a way to think about this definition up here is a low false negative rate. My handwriting is awful again, sorry. Low false negative rate. Because let's say up here is 10, and if the false negative rate was 0, it would be a bigger number than if the false negative rate was higher. Okay? So sensitivity is great. If it's high, it means it's great at avoiding false negatives. Let me give you an example. Sensitivity is good for screening. And in medicine, why is it good for screening? Because if your false negative rate is low, that means it is a great test to rule out a disease. Meaning, if a test is negative, the chances that they will actually be positive for it is almost nil, because of the false negative rate is very low, meaning a high sensitivity test has no information about the opposite, meaning if the test was positive, a high sensitivity does not tell you anything about how many false positives there would be. Meaning if a test is positive, it's not great at ruling in a disease. But if sensitivity is high and the test is negative, it is great at telling you they don't have the disease because the false negative rate is low. Specificity, on the other hand, is better at confirming tests. And again, I think that this definition here is accurate to this equation, but it doesn't help you in practical sense. And let me tell you why. To have a high specificity, you have to have a low false positive rate. Meaning that this test If you test negative, it doesn't mean that you don't have the disease, because the false negative rate could be very high, because this equation doesn't have a false negative rate. The false positive has to be low, meaning that if someone tests positive for this, the chances that they don't have the disease is very slim, which means it is a great test to confirm a diagnosis. Let me give you an example in medicine here. Let me flip this again. So again, you can look at sensitivity and specificity in so many different ways, but I promise you, if you actually route those equations and understand the first chart I showed you, those 4 possibilities, it starts to make a lot of sense. So let me give you an example. If someone has a blood clot in their leg, or you're worried about a pulmonary embolism, like they have a blood clot in their lung, a test you would typically start out with is something like a D-dimer. The D-dimer can be elevated for many reasons. So if the D-dimer is high, it doesn't mean that they have a blood clot. However, it's a very sensitive test, meaning that if it's negative, the chances that they have a blood clot are very, very low. Because in sensitivity, the false negative rate is very low. In other words, a sensitive test is great at predicting that someone doesn't have a disease if it's negative. And that is why in medicine, when we screen for tests, what we are doing is we're not necessarily as worried about the false positives. What we are worried about is making sure that that test is negative, that we don't need to worry anymore about checking that, at least for a year or whatever the recommendations are. So specificity is not what you want in a screening test. Screening tests are cheaper, and screening tests will cover everybody, because if they're negative, then that just kind of rules it out. In specificity, we're more concerned about the false positive rate, meaning we want to avoid the false positive rate. So let's take the example of the D-dimer again. So let's say the D-dimer is positive, but we doubt that someone has a blood clot. Well, then but we're worried about still, they're having a little trouble breathing, we're going to see if there is a blood clot. So we get a specific test that also happens to be pretty sensitive too. We get a CTA to actually visualize the pulmonary vasculature to see if there's a clot. And that test is very specific, because if it shows on that test that there is a clot in the artery, then there's almost 100% chance that there is a clot in that artery. So you want to use specificity to confirm a diagnosis, because a sensitive test could still have a lot of false positives, but a specific test won't. I want to flip right back again and show you just one thing. There are 4 possibilities here in any kind of test environment. You have 2 covered here, and you have 2 covered here, and they're all different. Nothing in these equations have the same numbers, meaning they are independent of each other. So when they say the percent of people with a disease that is correctly identified, what that is saying is that it's saying that a sensitive test is showing that it will capture all the positive people, which is true. But I think it's easier to clinically think about in the opposite way of saying that it has a low false negative rate.